Welcome. My name is Joe DeGlider, and my thanks to you for joining this presentation. I'd like to talk about work we've done in SAP to analyze high availability gaps of storage systems in our data centers, and our thoughts about improvements going forward. Most of my career has been, like yours, working in storage systems research and development teams. More recently, I joined SAP to work in their cloud services organization. So now I've been experiencing storage systems from the other side. Looking at storage systems from this perspective has been really eye-opening for me. I learned that I hadn't been hearing or maybe appreciating much of what the support organization in my previous companies were dealing with day in and day out. More than anything, this is what motivated me to share with you some insights gained in a recent study we made of storage-related incidents in SAP. But I'd also like to motivate you to think about this as well. In this presentation, I'll take you through some of the information that we've collected, as well as the thoughts we gained from that data. And before going any further, I'd like to thank Harsha Ravuri, Ashish Mahajan, and Frank Schmidt for their hard work on this study. And if you want to get in touch to talk about any of this, my email is on this page. Many of you may not know much about SAP, so I thought it would be good to spend a few minutes introducing it to you. SAP was founded in 1972 in Waldorf, Germany, and has been delivering business software ever since. SAP delivers business software solutions to a majority of enterprises worldwide. In fact, 77% of transaction revenue worldwide touches an SAP system. It's likely you're using one or more SAP solutions, maybe without even realizing it. SAP has over 100,000 employees in about 180 countries and delivers solutions to over 440,000 customers in close to 200 countries and in 25 industries. SAP is a very technically oriented company, and our yearly research and development spend is well over 4 billion euros and increasing. And for that investment, we earned over 27 billion euros last year and expect that to increase again this year. More recently, SAP started delivering its software via cloud services. SAP's business is centered around software, and one of the most important software products offered by SAP is HANA, our flagship in-memory database system that's used by most of the business solutions offered by SAP. SAP software spans the entire range of business solutions, and here are a few of the major products. HANA, our ERP solution SR4HANA, our customer experience solution C4HANA, and our analysis and insight solution SAP Data Intelligence. As I mentioned, SAP more recently started delivering its solutions as well through cloud services. These include infrastructure as a service offerings such as HANA Enterprise Cloud, platform as a service offerings like SAP Cloud Platform, and they also include software as a service offerings that you might have used, such as Concur, Ariba, and SuccessFactors. Many of these services are offered through our Global Cloud Services organization, which is where my fellow authors and I work. As I mentioned, cloud services are a more recent model for delivering SAP solution to customers, and most of these services are offered through GCS. GCS offers cloud services to SAP lines of business, which in turn offer their services to external companies. GCS operates somewhere in the vicinity of 30 data centers worldwide. And most recently, GCS is offering some of these same services as well via the bigger public clouds. However, the focus of the study described in this presentation was SAP managed data centers, where the infrastructure is GCS's responsibility. These data centers together offer large-scale cloud services. They currently contain hundreds of thousands of VMs, tens of thousands of hypervisors, and over 200 petabytes of storage. GCS Storage is the team in GCS that delivers block, file, and object storage to GCS data centers worldwide. We don't have an internal storage system development organization. Instead, we typically deploy traditionally designed, well-hardened storage systems that we buy from major vendors. Our experience has been that storage service has been the most stable in GCS. However, because our externally attached storage systems are often widely shared, unexpected storage incidents, although they happen very rarely, can have large impact. This is what motivated us to study these incidents, to gain insights on how we can reduce the impact of incidents in the future. First, a bit of background. When an incident occurs, a team is formed to track and manage the incident until its resolution. The team generally includes representatives from any groups within GCS that might be able to add information or insight, as well as representatives from vendors whose products might be involved. After the incident is resolved, a root cause analysis is performed by members of the team and a report is generated. It generally identifies root cause and contributing factors, as well as making suggestions for improvement. After the RCA report is released, there's generally follow-up to address suggestions from the report. Remember that our motivation for this study was to find ways that we can reduce storage incidents' impact without significantly increasing costs for the solution. So, for example, adding disaster recovery solutions, synchronous or asynchronous, for every piece of primary storage wasn't an option. It would more than double the cost. Instead of going that route, our idea was to initiate a different kind of study of the RCAs to look for areas of improvement. Instead of focusing on each RCA individually, as done before, we decided to look at them all together. We collected RCAs generated for the past several years, which spanned over the 2,000 plus storage systems and 200 petabytes, and we looked for common themes that occurred across multiple RCAs. And we did find common themes. Surprisingly, there were multiple occurrences of a single misbehaving drive triggering a chain of events that resulted in an incident. Similarly, there were other single points of failure in a chassis or shelf that resulted in an incident. We also saw multiple times that there was interference with regular I/O service in a controller, without detection by the storage system or automatic recovery. There were also some contributing factors that were part of the chain of events leading to an incident. A number of incidents were triggered by or occurred during an upgrade or maintenance process, and a number of incidents were helped along by human or process error. As a past designer of storage systems, I was surprised by these failure modes, and I thought you might be as well. So let me give you some more detail about some of these incidents. Concerning single points of failure, as mentioned before, we saw that a drive connected to multiple controllers acted in an unexpected way, such as with large bursts of errors, which in turn caused unexpected behavior in each of the controllers that it was attached to, and eventually led to an incident. We saw other single points of failure as well. Overheating of both controllers in a chassis caused by a common component affecting multiple fans. An exception in a CPU in one controller propagated by the common bus to the other controller, causing a similar exception. Concerning I/O service interference, we found that certain conditions can interfere with proper I/O processing in a controller without it being detected by any system self-check. In one incident, we saw network traffic stop for one port without it being detected or auto-recovered. In another incident, failures of a local logging device interfered with I/O processing without auto-recovery. In yet another incident, a memory leak interfered with I/O processing, again without auto-recovery. Human and process errors in multiple cases resulted in procedures not being carried out in line with best practices. Sometimes not performing all checks necessary, sometimes neglecting to complete a required step, sometimes incorrectly executing a step. Specifically during upgrades, we've seen unexpected scenarios play out. Considering that upgrades and maintenance windows are times when humans or process gets most involved with the system, it's not surprising that the two factors might combine and result in an incident. Sometimes incidents occurred because of hardware issues encountered during the upgrade, and sometimes something was changed either as a result of the upgrade or within the upgraded firmware itself, and that resulted in the system post-upgrade being unable to fully function. Having identified some patterns among these RCAs, what do those patterns tell us? And can we leverage those insights? Can we expect that having followed through with all the guidance from the RCAs, we will experience less incidents going forward? Unfortunately, we suspect that's not the case, and the evidence from the last several years has been that our incident rate is more or less flat. I found this diagram. Frankly, I've seen similar ones over the course of my career. To me, it suggests this. History is telling us that defects in software and hardware appear with every new release. And as the hardware and software become more complex, it becomes more difficult to thoroughly test every corner case, which then leads to a rising baseline level of defects and a higher likelihood of incidents due to unusual and untested combinations of events. So, given this reality, are there choices in architecture or design that could lead to fewer system vulnerabilities? And can the patterns that we've observed inform those choices and result in a system that doesn't increase system cost? Here are some of our thoughts, and we'll be very interested in hearing yours as well. Concerning human process error, this probably doesn't surprise you, but fixing humans doesn't seem to be a winning strategy, so taking them out of the equation looks to be very important. More automation wherever possible, and where humans need to be involved, make it simple, make it well guided, make it well tested with real operations staff. Backdoor configuration by vendor support teams shouldn't be used because it can interfere with upgrades down the road. And we have great hopes that proactive analytics, otherwise known as artificial intelligence operations or AI ops, will take a lot of humans out of the equation by making all the good insights that come from the global worldwide experience available directly to customers without having to go through a chain of humans in support and operations organizations, or by detecting conditions early and getting them resolved before they combine with other conditions in a bad way. Concerning upgrades, the top statement on this page says it simply. We want to be perfectly confident in getting successful upgrades, and we don't think we're there yet. But I have hope. 10 years ago, I sweated before I pushed the upgrade button on my smartphone, and now I don't think twice. One point to bring up here is that upgrade methods today often result in more vulnerability during the upgrade. First, human interaction is part of the upgrade process, and the act of upgrading often leaves the system being upgraded without redundancy during the upgrade sequence. For example, by putting a controller into maintenance mode for minutes while it's being upgraded. Can upgrades be designed that retain some redundancy through the entire sequence? Certainly, scale-out storage systems offer that. They only upgrade one controller out of many at a time, all the while the system retains most of its redundancy as well as most of its performance. Can upgrades be zero-touch while doing complete compatibility checking? Can upgrades be designed to never have dependencies or restrictions or disruption? Concerning surveillance of storage systems, HA storage systems have a great deal of internal checking and automatic recovery, but we've seen that it's not perfect. Would it be useful to think about an external agent that can also look for anomalies without introducing enough extra complexity to make the whole system less rather than more reliable? There are some examples of witnesses or tiebreakers or mediators that might provide one pattern of deployment. Perhaps proactive AI ops already offered by some vendors can include this extra oversight capability at very little extra cost or complexity. HA pairs, especially where the two controllers share common components, can contain subtle vulnerabilities. These could include direct connections between controllers via buses or otherwise, drive shelves connected to all controllers, drives themselves, backplanes or midplanes, power systems, cooling systems. And as mentioned before, when an upgrade of an HA pair leaves the system with no redundancy while the controller is in maintenance mode, it can be more of a vulnerability than we'd expect. Thinking about all this led me to a question about HA pairs. Scale-out storage systems have certainly gained a lot of traction over the past several years, but I think that HA pair is still the dominant high-performance deployment model. However, I remember when RAID 5 first came out. It satisfied the market for some time, but as scale of deployment increased, there were significant numbers of cases where RAID 5 was not enough. And so the requirement grew for redundancy from multiple media faults. Likewise, with the scale of complexity of today's IT, is the single fault redundant HA pair controller system the best solution? Let me divert your attention for a moment to look back 40 years. I started working for Memorex in 1979, which at that time built storage systems for IBM mainframes. Don't be confused, Memorex was known for more than Ella Fitzgerald and consumer tapes. In fact, at that time, Memerex's strategy in the mainframe storage market was to deliver more advanced function than IBM was building into their storage systems. Around the time that I joined, Memorex had just delivered the world's first dual intelligent string control storage system for the IBM mainframe market. To explain the picture you're looking at, the units to the left of the woman are 3330 disk drives, each with the huge capacity of 100 megabytes. The woman's left hand is on a 3673 disk controller. The other controller can't be seen in this picture, but would be all the way to the left of the string of drives. Also interesting, and a little bit of an aside, the woman's right hand is on a 3770 unit, the world's first commercial disk cache. And by the way, the patent for it was initially held up because of prior art. The patent examiner found that it read over a patent for a toilet with a holding tank for water. Really, true story. And one more digression. A vertically oriented package of a newer generation of those systems you're looking at almost fell through the floor tiles. But back to the subject. You folks all know what a storage system looks like today. Maybe 1/100th the size and about 100,000 times the capacity compared to the 1980 era system I showed you. The HA pair architecture today, although it shrunk to something we can pick up without too much trouble, is fundamentally similar to the floor tile breaker of 40 years ago. So I did this estimation that you're looking at, most of it from my own memory, maybe not all correct, but I think within an order of magnitude or so. This table shows what I think are the most relevant factors driving overall reliability and availability: hardware MTBF, system complexity, and scale of deployment. Hardware MTBF has actually improved in the last 40 years. The 14-inch disk drives that were as big as washing machines were pretty reliable compared to the 3.5-inch SCSI drives that came out in the 1980s. But the reliability of hard drives and SSDs have become much more so than that today. Similarly, controllers for disk drives in 1980 were 5 to 10 or more boards with lots of discrete logic on them connected together via wire wrap backplanes. And probably back then, connection issues were the biggest source of failures. Now most of this is combined into a few ASICs on a single board, so I believe the reliability is much better now. Then there's the question of complexity. The number of lines of code has skyrocketed for my first controller that held 4,000 16-bit instructions. And of course, the number of gates in the hardware has increased by many orders of magnitude as well. Lastly, there's the question of scale. I remember large data centers in the 1980s that just had a few dozen drives and several controllers sitting alongside the few mainframes. Whereas I showed you the scale of storage systems today in SAP data centers, thousands of storage systems with tens of thousands of drives. 40 years later, the result is that the factors that would tend to increase likelihood of incidents are huge compared to the factors that would tend to decrease likelihood of incidents. Storage system hardware failure rates might be on the order of 10 times lower, but scale of deployment might be on the order of 250 to 500 times higher, and complexity of the storage systems might be on the order of 100 to 250 times higher, and I think that's probably a very conservative guess. While I'm not going to pretend to be able to put this into some equation, I think that the contrast between the positive and the negative influences are compelling. No wonder we see regular occurrences of failures that are auto-recovered, but more importantly, occasional incidents that we have experienced. So, some final thoughts. Data availability will, of course, continue to be critical. Cloud-native apps built on the premise of availability zones may handle data availability differently, but for high performance, separate copies are needed in each availability zone, along with high network bandwidth, and those both can be costly. Also, we expect that many critical enterprise apps will continue to rely heavily on storage systems that deliver high performance access to the primary data copy. For those category of apps, to minimize impact of storage system incidents, we can essentially do two things: shrink the impact zone affected by an incident, or shrink the number of incidents altogether. Shrinking impact zones is not easy. We again have two choices: use smaller systems, which will drive up cost, or have an effective way of partitioning large storage systems into fault zones to isolate impact of disruption to a single zone. But we need to prove to ourselves that there is no way for the entire storage system to be the scope of an incident. And from personal experience, I know proving that won't be easy. I've tried. So our other choice is to decrease vulnerabilities of storage systems to achieve smaller numbers of, and ideally no incidents, either through the design of the system, or through design of how the user interacts with the system, or through how the system is proactively monitored. At SAP, we'll concentrate on all of these. As we move forward in our storage system evaluations, we'll be putting much more focus than we have before on subtle single points of failure, on artificial intelligence operations, and on minimizing human interactions. And with that, I thank you for your attention. We'd really like you to ask questions or leave comments in the Slack channel, and we'll certainly respond. And make sure to write this session.